in sediment mechanics laboratory, what we do there is we look at the dynamics of earthquakes. So fundamental questions like how do earthquakes get started, why do they stop, and why do some faults have different types of earthquakes? So to do that, there's a lot of numerical analysis, we do a lot of experimentation, and then of course a lot of analysis of natural data because we are trying to model the real world after all. The specific piece of that I'm going to tackle this morning is what we call rate and state friction. It's the most accurate way we have right now of understanding how friction works beyond the simple physics 101 explanation of static friction and kinetic friction. We know that's a lot more complicated than that. The longer two things sit together, the stronger they become through a process called frictional healing. It's a common problem in engineering, especially when you're trying to launch ships. That's when it was first discovered, actually. And then, of course, velocity dependence of friction, which is kind of a second or third order effect that I'll show you. On the title slide here, see if I can use my pointer. No, there we go. We've got that top left plot showing you in the black line a system that is stably sliding, hence the black line being flat, and then becoming increasingly unstable, each of those oscillations representing an actual earthquake in the numerical model. You can think of the y-axis as friction or shear stress. And then those changes in shear stress actually create elastic waves that propagate throughout the Earth, and that's earthquakes that we record on seismometers producing the waveforms shown at the bottom there. Anybody that's seen me give a talk at an academic conference knows that I really like alternate titles, so I figured there would be no exception here. You can also consider this, if you're not into rate and state friction, as avoiding common academic software slip-ups, which seems appropriate for friction, especially with that picture there. So before we can get to how we solved this with Python and show you the implementation, I have to give you a little bit of background, kind of an earthquakes 101 for those that aren't geoscientists in the room. Then a little bit of frictional theory, show you the system that we're going to try to solve, introduce the equations and how we actually have the best conceptual model of this, and then the Python implementation of how we've done this to be effective as a research and a teaching tool. So the very basics of earthquakes. We have about a dozen tectonic plates that make up the globe, and earthquakes generally occur at the intersection between these plates where they subduct or push beneath each other, slide past each other. We've got the major earthquakes, the ones that would matter, you could say, from 1980 to 2015 plotted here. And you can see those plates outlined pretty well. Now, some of these boundaries actually don't produce any earthquakes, so there's no dots here. We would call that a stable fault or an aseismic fault. It just means that the plates and the sides of the fault creep past each other slowly. They actually don't stick and store energy. If we were to make a plot of this through time, you would see that shear stress builds up as the plates move. They're moving somewhere between the rate your fingernails and your hair grow, so pretty slow, 4 to 6 inches a year, until they reach some failure stress or failure friction, however you want to formulate it, and just you get a flat line, like I initially showed in that plot on the title slide. Now, just because they creep and don't create earthquakes, it doesn't mean they're not risks for infrastructure. This is the California Memorial Stadium on the left there, and you'll see that offset, and that's not supposed to be there. That building is actually being sheared about 2 centimeters a year because the Hayward Fault runs directly diagonal underneath it. So that's a problem. You can also see on the right photo the curb that is offset by the Hayward Fault. And believe it or not, that has actually just been fixed in the last week because Public Works fixed every geologist's favorite curb and not all of the other ones. So the more interesting way that faults can fail, that as geoscientists we generally get really excited about, is in a dynamic or unstable way. So in this case, we're applying the same loading rate. You see that the shear stress builds up, but when it reaches a failure stress, instead of just sliding stably, all of that energy is released at once, or some large fraction of it anyway, in a pretty catastrophic fashion. So in that stress drop, that rapid shear stress over a change in time, we get those propagating elastic waves that are earthquakes. There's a lot of things we don't understand about this. We don't understand exactly how much of the stress drops still, and we've been studying earthquakes in depth for at least 50 years in modern digital seismology. But if you're not into earthquakes, that's okay, because there are a lot of other applications that you can use this friction framework I'm going to show you to solve. Engineers have cared about rate and state friction for a long time because earthquakes are actually just a stick-slip process if you're an engineer. So the two materials are statically held together and then rapidly fail. When you're drilling and you hear a sound or machining, there's vibration. That's a stick-slip process in a machine. if you're into biology, animals use stick-slip processes, which are the exact same physics, to make noise to attract others or to ward off predators. And we've thought of earthquakes as stick-slip for maybe, I don't know, since the 60s at best, kind of before literature got increasingly siloed, unfortunately. Okay, so a little bit of frictional theory. We're trying to model a complex fault in the Earth, and that is obviously beyond our reach. So this is the system that we're going to model. As I'm going to show you, it's still pretty complex and almost beyond our reach. We've got a motor over there on the right that's going to represent plate movement, so loading from the tectonic plates. There's a spring in the center that represents elastic rocks surrounding a fault zone. Or if you're an engineer, it's the stiffness of your milling machine or whatever you're working on. And I know rocks don't seem elastic, but if you hold a cube of granite in your hand, say it's a couple inches on a side, and squeeze it as hard as you can, you're actually making it shorter by about 1 micron. And that doesn't seem like much, but we can measure it, and that is where all of the energy for earthquakes is stored. It's in these very small amounts of deformation in rocks and a couple % strain. And then we've got a slider over there on the far left. So where the slider interacts with this sliding plate, that's our little experimental fault. When you see people talk about rate and state friction, they show this, and then they show some plots, and that's what they do, but I thought it'd be fun to actually show you what the physical system does. So we built one, because granite's cheap, and so are windshield wiper motors. So what you're going to see here, I will press a button, there we go, and this block just slides along stably. So this is an aseismic or creeping fault. You also notice there's no spring, it's just the stiffness of that piece of string. It's relatively stiff, so the system has a pretty boring behavior. But now just a few minutes later, I reset, and I put a spring in series, and you see the behavior of the system completely changes. The block is now sticking and slipping, each of these being little bitty earthquakes. If you were to calculate the magnitude of this, it's about a magnitude -3. So now I'm going to show you how we can model this. This is the state of the art, if you will, in modeling friction, which is a little scary. So we've got a derivative for friction with time, and it depends on all these empirical parameters. There's one that's creatively named A, and that is the direct effect, which is a transient after you perturb a system, so you change how fast you're pushing or pulling on it. And then next, we have B, which is the evolution effect. So what the new steady state friction of the system is going to be after the perturbation. And there's obviously some kind of time scale or slip scale that we have to do that evolution over. We call it D sub C, the critical slip distance. And then there is the state variable theta, which we could argue as scientists a lot about what that actually indicates. And I'm going to show you there's a lot of different relations for it. People generally think it has something to do with the age of the contacts on a fault. And an elastic coupling relation, because we have to get stiffness in there somehow, which in this case is just really simple, linear elastic, 1D, and not representative of the Earth at all. But that's how we do it. So state relations. These are a few that are out there in the literature. Everybody has their favorite. You're trying to model maybe frictional healing, so one works better than the other. The aging law at the top, for example. The slowness law might fit your experimental data better. Or you can add another free parameter like at the bottom. You can add C, because more free parameters, you're going to fit your data better. But does that actually physically mean anything, which is, of course, beyond the scope of what we're going to talk about here. Just show you that those are there, and we do have all of those included in this model. Okay, so as a scientist, what we do is we run these models to try to make designs for experiments that we do in the lab on machines like this. These are giant hydraulic presses. We actually use Python to control part of this, which is really fun. Putting 1 meganewton of force on rocks and creating earthquakes in the lab. And this quote, I don't know who to attribute it to, but I think it's very relevant for all of experimental physics. That theory is when you know everything but nothing works. Practice is when everything works but you don't know why. And in the laboratory we combine those so nothing works and nobody knows why. All right, so now the modeling part actually. There are several rate and state programs out there that different people have developed during the course of their graduate work or postdoc, what have you. And I think I've come up with a recipe for how you create a rate and state program or a lot of scientific software. And I'm as guilty of this as anybody else. You take numerical recipes in your favorite language, be it Fortran C, or better yet, your advisor's copy, because it is expensive. You take the textbook that has the governing equations, mechanics of earthquakes and faulting. You take coffee, and you take a conference deadline. You put all of these together and you work feverishly for multiple nights to come up with some piece of code that, in this case, there are actually comments there, so yeah, that's good. But it's probably not maintainable, it's not scalable, it's definitely going to be not tested, or there's no documentation out there. So then you write the paper, or you present the abstract, and somebody says, well, I want to reproduce your results, or I want to compare your model to my model. And a lot of times when I've done this, you get things like this back. These are completely contrived examples to not put anyone in front of the bus. It's hard to see because of the projector, but that bottom left one, there's a commented line that says, only works with this commented out question mark. You see a lot of that. Or you get this giant zip file that's, here's everything I did for this paper. And when you unzip it, you see things like data, data 2, model with bug fix, why didn't this work, run 12. And then you try to compare your model to this, and you talk to somebody and you say, what did you run? And if it's more than 6 months since the paper came out, they probably don't remember either. And you both walk away saying, well, this has been an interesting encounter. So if you look through the literature, we're all trying to solve the same problem, right? These basic frictional dynamics of systems. We all plot it in slightly different ways. These are just a few examples that I pulled. There's not really been any comparison between these models that folks have, which is a little shocking, right? Maybe the different numerical methods that we're using are introducing different errors. We have no real bounds on that. In fact, some of these have been, in the early 80s, where they only ran a dozen models because that was the limitation of the computing power at the time, whereas now we can do a few 100,000 in the same amount of time. So when you look at this, you say, or at least I said, but there are no tests. There's nobody that has directly compared these. And the tools aren't friendly to students either, which is, as an educator, what we really want to shoot for, in addition to doing research. This is one of these rate and state tools that's out there, the man page, if you will. I know it's too impossibly small to read, but it's a little scary if you're an undergraduate student and you get handed this. You're trying to understand a concept that's completely foreign to you, and then you have this thing that you need to learn how to use that's not intuitive at all, because first you have to find a program called Terminal on your Mac that you didn't know you had. And if you don't have a Mac, you find somebody that has a Mac, you open Terminal, you run this, and then you get a text file out. And you don't really know how to work with text files, so you import it into Excel, and you make a plot that's got drop shadows and cool backgrounds and all kinds of things, and then you put it and turn it in. You spend a lot of time dealing with the tool and not a lot of time learning. And as a researcher, you still spend a lot of time dealing with the tool and not as much time exploring the system as you'd like. So the requirements for this were really simple. I had to be able to use it for research because that was what I was getting paid for, after all, to do during the day. I wanted to be able to use it in classes for teaching, which we're going to try this year. And then had to follow software best practices, which Ryan is going to talk about extensively after this. He was involved with this, so I'm going to not touch on that anymore. So here's an example of using this modeling tool, RSF model. First, you just have to create a model object and then set some of the attributes, like that A parameter, the stiffness. All this is relatively simple if you're familiar with Python. And then pick your favorite state relation. We have all the common ones in the library. And set its parameters. And then you just pass a state relations list. People do use multiple state relations sometimes in their modeling. This lets you mix and match however you'd like. Give it a time and velocity vector that you would like to solve for, and then call model.solve. Now you have a fully populated results object that you can query. But you don't have to write your own plots or anything like that, because we do that as well. You need to say things like plot.phaseplot to get one of my favorite ways to look at solutions to differential equation systems, the phase plot. If you have multiple state variables, where you need to have multi-dimensional phase plots, so you can get up to a three-dimensional phase plot out, it'll intelligently pick that for you. And then the more standard plots that you might want to more intuitively look at, like how does friction evolve with time? How does state evolve with time? Those kind of things shown there on the bottom. We also want to allow users to define their own state relations, because sometimes you have an idea of, well, maybe if I tweaked this in the state relation, it would be more representative of some physical process that you are trying to understand. But if you're using your grand advisor's C code or something, well, how do you work that in? Because it's probably not functionalized very well, or maybe it's integrated into the numerical method. Well, here you just define a class that, in this case, my state relation. You provide methods for setting the steady state, the initial condition, and then we call it evolved state, but it's just d theta dt. You provide the derivative. And to use it, all you have to do is call it, set its attributes, and then put it in the list. So in just a few minutes, you can mix and match state laws, you can tweak things in state laws, and as long as it's something that's numerically solvable, you'll have a result. The entire thing is tested. We've compared it to at least one other model. We're trying to do a comparison to another one now, and created a set of standard test cases that we'd like people that are involved in this field to use and to contribute to, and then we check it every time. It's not like the traditional academic software model that has been shown in PhD comics of, did you check it? Yes. Did it confirm the hypothesis? Yes. Then go on. In the process of doing this, we found some really interesting things. There was a relatively well-established result, if you will. From experiments, we've seen that the time between earthquakes and how fast we're pushing is directly related to how big the earthquake is. That might make intuitive sense. The longer between earthquakes, the bigger it should be. And a numerical modeling study said, yes, these equations can predict that, and we understand how this works. That's fantastic. And we've cited this for some number of years. But while playing with this model, those three plots on the right are from the same physical setup of the model, just slightly different ways to introduce perturbations. And you can see the scale on the top two are different. And the bottom one, the model is completely stable. There are no earthquakes at all. So that means that that plot from the literature on the upper left, that beta 1 trend, we can make it go up, we can make it be flat, or we can make it go down. It's completely dependent on how you set up the model. So we understand maybe conceptually how this works, but numerically, we don't have support for it. And that's because it was really easy to play with all these parameters. And this is the reaction when we found this from a lot of our coworkers, because we've all leaned on this kind of knowledge for a long time, and it's not actually there. All right, so in the last few minutes, I want to show you how we're going to hopefully allow ourselves and our students to play with this using the Jupyter Dashboards project, which is in the incubator right now. You can go and play with it. We've had pretty good luck so far. So we will do a live demo. You can go to rsfmodel.com. Right now, that directs you to the GitHub page. Hopefully, in the next maybe day, maybe 2 days, it's going to direct you to an AWS instance where you can play with this dashboard online and not have to install any of this on your machine. So now for a hopefully live demo. This is a notebook, but using dashboards, we were able to hide the code cells that you don't need to see, and then just drag them around to create this user interface. So this hopefully will be, like I said, on AWS. You can play with it. We've got buttons, we've got plots. Of course, you can interact with these and zoom. And up here, you can see the mouse. On the upper left, we've got a couple of critical parameters. This is a stability parameter, you can think of it as. If it's over 1, we're stable. If it's under 1, we're unstable. And now we can explore. What happens if we make the system a little bit stiffer? Well, we know it should go more into the stable realm from those videos earlier. We press calculate, and you really quickly see, yes, the friction does evolve to a steady state more quickly. We don't get any of these oscillations. The phase plot looks significantly different. We can add a second state variable if we'd like. And that changes the behavior of the system somewhat. So it's really easy and really quick to be able to do these explorations. And as a student, you're not worrying about how to use the tool. You can just click save, drag these plots right into your report. We can also show some of the more fundamental things like, so right now we're just specifying the perturbations and velocity displacement, so how fast we're going and how far we're sliding. Let's say we want to do velocity time perturbations. So let's simulate sliding something, stopping for 10 seconds, sliding again, and then stopping for 100 seconds, and then sliding. So I'm going to show you frictional healing. So we're going to slide for, say, 10 seconds, stop for 10 seconds, slide, stop for 100, and slide. And now we see this interesting behavior that when we held for an order of magnitude longer, the frictional healing was twice as large. That's a really easy way to show a student this and let them play with it. And they can say, well, what happens if I use somebody else's relation? Well, that changes the behavior significantly. Why is that? Which one of those could be more physically valid? These are all discussions that you can have in class now pretty easily. And of course, we're still playing with tweaking the interface and letting this be a little bit more usable. But I hope what you got out of this is that there's ways to make scientific software usable for research, usable for our students, and without a whole lot of effort, make it reliable. So thank you.